Okay, good morning, afternoon, everybody. So today's lecture, we're going to cover structures a little bit more in detail than when I first introduced them. Okay, so remember what a structure is in C. It's basically the C programmer's mechanism of creating a new type, right? So it's sort of like a Java class where all the fields of your class are public, right? Of course, there's some differences. Your structure doesn't have any member functions or methods, right? And a structure has no constructors. So initializing the structure is up to the programmer. And if you want to create things that look like methods, basically you create C functions that accept structural objects as their inputs. So we saw the declaration of a structure, I guess, a few lectures ago. So remember, when you create a structure, it's the keyword struct, and then you give the structure a name. So that's called a tag in C, right? Your members, or your quote unquote fields of your structures, they just go inside of the braces after the structure when you actually define the structure, right? And so we had an example, our point2 structure from the previous from a couple of lectures ago, where every point2 has an X and a Y coordinate. Okay, this is a little bit new, so I haven't talked about dynamic allocation yet. We're going to get there in a lecture or two. But now that we know about pointers, you can make a structure object and then create a pointer to that structure object. If you want to dynamically allocate that structure object, then you use this function called malloc. So malloc is like the new operator in Java, right? So it's the thing that allocates memory for a new object in C. Right? So malloc, it doesn't actually create an. All malloc does is give you a chunk of memory of a specified size. So to store a structure, to store a point2 structure, I need to know how much memory does that point2 structure take up in memory, right? And the size of operator can compute the size of a structure because of the way that structures are defined, which I'll explain in just a minute. So size of, round bracket, struct point2 tells you how much memory is needed by one struct point2 object. Malloc allocates or attempts to allocate enough memory for however much that quantity is. So this is asking malloc to allocate enough memory for 1.2 structure object. And then P, malloc, if it succeeds, returns a pointer to the allocated memory, and now P is a pointer to that structure object. Right, and so that two lines of code that allocates that creates a pointer to a structure. The second line creates the structure object and sets the pointer to point at the newly allocated object. Again, we're going to come back to malloc in a couple of lectures when we talk about dynamic memory allocation. So remember, initialization you can do using the braces, right? And remember, you can only do this at the point of declaration, right? So when I declare P, I can also initialize it, right? You can't use the initialization syntax for assignment. You have to do something else for assignment. Right, so that initializes our point to have coordinates 0.1 and 0.2, right? If you want to, you can be a little bit fancier. You can explicitly say what X and Y, or what 0.1 and 0.2 correspond to. So you can use the name of the members in the initialization here as well. Right? If you think I'm going too quick, it's because we did cover this a couple lectures ago. And finally, to access the structure elements, the members of the structure, you use the dot notation, right? Same dot notation that you use in Java. So here's my structure defined up here. There's initializing a structure P. So it has coordinates 0.1 and 0.2. That returns the value of the X coordinate of P. Right? That returns the value of the Y coordinate of P. These two lines set the X and Y coordinate of P. Now, we know about pointers. So if you have a pointer to a structure, right, you can still access the members of the structure, but there's a special syntax that you can use if you have a pointer, right? So if you don't have a pointer, so you just have a variable P that contains a structure object, you use dot. If you have a pointer instead, you can use the arrow with the pointer, and the arrow with the pointer will dereference the pointer for you and then give you back the object corresponding to the underlying member. Right. So similar example here. Here I'm going to dynamically allocate a structure object here. I guess if you don't like that, we can change this. So let me change this because we haven't really talked about dynamic memory allocations. Let me do something else. Struct point to p equal p. No, we can't use pq equals. So I'm going to make a structure. I'm going to make a point whose coordinates are 1 and 1, like that. Right. And then I'm going to take a pointer to that structure. So struct point to. I want a pointer. So star. Right. P is going to be my pointer name. It's just going to point at q. So I'm going to do that instead. Right. All right. Now using the pointer, right, I can get to the x coordinate of the point by first dereferencing the pointer. Right. So star p, dereference the pointer. That gives me q. Right. And then I want to write dot x to get to the x coordinate of point q. Right. Unfortunately, if you try to do that, you'll get a syntax error because of the precedence rules. So it turns out that the dot operator here has higher precedence than the dereference operator. So you have to do the dereference first inside around brackets, right? And then you can take the dot or apply the dot operator to the result, right? So all of that is equivalent to q, and so that's q dot x equals 100. So that changes the coordinates of the point, the x coordinate of the point to 100. That changes the y coordinate of the point to 200, right? And if you run that, right, you see in fact that the coordinates of the point have changed to 100, 200. Right. Now, this is a bit clunky to write. Right. Having to dereference inside of parentheses followed by the dot is a little bit awkward to write. So instead, you can use the special arrow operator. So if you have a pointer to a structure, you can dereference the pointer and access a member all in one shot. You write hyphen greater than. So pointer hyphen greater than, and then you access the member with just the name of the member. Right. And so that does the dereference for you to give you the member x belonging to q, and you can change that to minus 1.5. Right. Again, dereference p to give me the object q, and then give me the member y belonging to q, right, and set that to minus 2.5. Right, and you can see that that also works. Right. So if you have a pointer to structure, using the arrow operator is a little bit easier than writing round brackets and dereferencing the pointer yourself. Right, but they both work just fine. So if you really don't like the arrow operator, you can always dereference the pointer yourself manually. All right, so assignments. This is where the analogy of a structure being a Java class kind of falls apart. So you can assign a structure object to another structure object in C. Now, remember what happens if you assign a reference to a reference in Java, right? So in Java, if you make a, I don't know, like a date, right? So you make a date D, you make it some date, and then you write date E equals D, right? That doesn't actually make a new date object, right? That actually creates two references. Both references refer to the same date object in Java. That's not what happens in C, right? So in C, if you write something like Q equals P, where Q and P are both structure objects, then what ends up happening is you get a brand new structure object Q that is a copy of P. Right. So assignment works the way assignment works for primitive values in C. Right. You actually get a new object. It gets the value of the copied object. So in this case, Q is also the point 1, 2, and they're two independent objects. Right. If you modify P, Q doesn't change. If you modify Q, P doesn't change. Right. So that's very different than what happens in Java. Right. So there is my assignment right there. Right. You can also initialize via assignment, right? So struct point to r equals q. There are now 3 structures. All of their coordinates are 1, 2, and they're all independent from one another. Right. So if you run this program, right, P, Q, and R are all 1 and 2. Do I try to change it somewhere? Okay. So if you try to change one of the structure objects, so r dot x equals 100, and then reprint out the point. Let's reprint out all the points. The only object that changes here is R. Right, so notice P, Q stay the same, R has now changed, right? And so that's very different than the way things work in Java, right? Because Java, all objects are of reference type, right? This sort of thing where you do Q equals P, for example, doesn't actually make a new object in Java. In C, if it's a structure, you get a new object. Okay, so how does the copying happen? So it turns out all of the memory belonging to P. So when you write Q equals P, what happens is all of the memory that belongs to P, so that memory includes the two double values equal to 1 and 2, all of that gets copied bit by bit into a new structure object. So Q is what we call a Q is what we call a bitwise copy of P. Right? All of the bits belonging to P are copied, and now Q has a bitwise copy of P. Right? The same thing happens here. Right? All of the bits belonging to Q get copied, and they get and R gets the value of that copy. Right? So bit by bit copy, and you have independent objects when you use assignment with structures. Right? The same is true regarding, so if you have an array, a structure that has an array inside of it, the array also gets copied. So here's a structure called course info. Right? So the course info is just going to store a Queen's course code. Right, so something like CISC 220, right? And it's going to store that in a string, right? So this is an array of car, right? And it turns out this is an array of car of size 16, right? And then it also has a title, which is also a string, which in C is an array of car, and in this case, it's an array of car of size 256, right? That should be long enough for any course code at Queen, any course title at Queen's. Right. Don't forget, these are strings, so at the end of every string, there's a null terminator character. So how do I initialize, or how can I create an object of this type? Well, my type is struct course info. Right. Here's my variable C. Right. And now I can initialize code and title if I want to with any strings that I'd like. Right. So here I'm going to use the string sys220a and the title of system level programming. Right. If you print that out, you will get, not surprisingly, sys220a system level programming right there. Right. Okay, so if I create a new course info object I, right, and I initialize it by writing equals C, right, I get a bit by bit copy of everything belonging to C. Right, everything that belongs to C is all of this stuff here. Right, so the memory allocated to my first course info object is some array of characters, as two array of characters. Right, all of the contents of that memory get copied, and I becomes an independent copy of C. Right, so I can go into I. Right, I can go into its code. Right, and I can change the A to a B like that. Right, then I can go into I. Right, and I can make all of its. I can turn everything into uppercase. Right, so instead of capital S system level programming, I can make it all caps system level programming. Right, how do I do that? Oh, I haven't told you how to do, we don't really know how to work with strings yet. This isn't a great example at this point in the course. Okay, so what's going to happen here is I'm going to make a pointer, and I'm going to make it point at the first character in the array called title. Okay, so there's my array title. If you use just the name of the array, and then you can assign that to a pointer, that gives you a pointer to the first element of the array. Right. I would now like to iterate over the letters in the array, right? So I want to iterate over that. Right. More precisely, I want to iterate over that. Right. The title belonging to C. Sorry, to I. Title belonging to I. Right. So I want to iterate over all the characters there. Right. So the way I'm going to do it is a bit funny. So normally what you would do is you would get the length of the string, and then you'd write a counting style loop. Right? In C, you don't have to do that. So remember that in C, every string is supposed to end with a null character, right? So if I have a pointer to a character, which I do right here, right, I can simply move the pointer until I get to a character that turns until I get to the null character, right? The null character's value is 0, so that's equivalent to comparing a pointer to the value 0. So in other words, it's equivalent to testing whether or not this pointer is null, right? So that line of code there says, well, the pointer letter is not null, right? Dereference the pointer, so that gives me one letter in the string. Use the toUpper function, which is defined in, where is it defined? I think it's defined here in string.h. Right, so that takes a car, converts it to its uppercase version, right, and store it back in the car that's pointed at by letter. I haven't shown you how to do this yet, but it turns out you can add 1 to a pointer. If the pointer is a pointer into an array, it just moves the pointer to the next character in the array or the next element in the array. Right, so that simply advances the pointer so that it points at in this case the second character of the array. Right, the loop runs again. Right, dereference the pointer. That's going to give you a y. Sorry, a y. We're going to turn it to uppercase, so that gives you capital Y. We're going to store it back into the second place of the array. Right. Move to the third letter in the array, and so on and so on and so on. Right. We'll come back to this example when we talk about strings and arrays in the next couple of lectures. Right. But notice what it does. It actually does convert all the characters to uppercase. And finally, notice that by changing I, C remains unchanged. Right. So if you print out C again, right, the original course info object is unchanged. Right. So you really do get a new independent course level object every time you do assignment. All right. Now, what happens if the structure has a pointer member? Right. So inside your structure, I'm going to change course info so that instead of an array of car, I'm going to have a pointer to car. Right. So the course title, in this case, is going to be dynamically allocated. Right. So in other words, someone is going to allocate memory for the title before they fill in the title every time they use the structure. Right. The difference here is that instead of an array, you now have a pointer. Right. So what memory is occupied by one of these objects? Right. Well, you have 16 cars, plus you have one pointer. Right. When you copy this object, you're going to get a copy of the 16 cars, and you're going to get a copy of the pointer. Right. But you don't get a copy of the thing that's pointed at. Right. So in this case, if you copy a course info structure, right, the titles are not independent anymore. Right. You've got two pointers. The pointers are equal, so they point at the same thing. So if you use one object to modify the title, the other object is going to see a modified title. Right. So to use this one, you have to allocate memory for the title yourself. So I'm going to use malloc in this case. And then I need to copy a string into the title. Right. So the way you copy a string is with the string copy function. We're going to see this again in the next lecture as well when we talk about strings. Right. So string copy copies that string into that array there. Right. So if you print this out, you get the exact same thing as before. You're going to get C equals sys220A right there. Right, system level programming. I'm going to do the same thing as before. I'm going to change, so I'm going to make a copy of C, right, by using assignment. I'm going to change the A to a B. I'm going to change all the letters to uppercase, right, and then I'm going to print out the copy, right, and then I'm going to print out C again. Oh, wait, sorry. Okay, so there's my copy, right? Notice everything is in uppercase. Notice the A has become a B, right? So the course code, I changed that manually, right? The A to B. Now notice what's happened to C, right? So in C, the code hasn't changed, right? It's still an A, right? It didn't change because when I copied the object, I got a copy of its array, right? So when I modify code here, right, it modifies the array belonging to the second object, not the array belonging to the first object. right? But notice that C's title has now gone into all uppercase, right? And that's because the title is being stored via pointer, which in this case means C and I both share the same title. Right? So you have to be a little bit careful here when you're using pointers to stuff, right? So this is the situation that you run into in Java, right? So in Java, when you if you have an object that has a reference inside of it, and you do something like copy the reference by saying A equals B, right? You don't actually get a new object, right? You just get a new reference that points to an existing object. This is the exact same thing, right? So when you copy a pointer, you don't get a new object that's pointed at, you just get a copy of the pointer. Okay, so what about structures? Can you pass them and return them from a function? The answer is yes, right? The structures just get treated like any of the primitive values. All of the bits of the structure get copied and passed to the function, right? So the function gets a copy of your structure. If a function returns a structure, all of the bits of the structure get copied and returned back to the caller, right? So the caller gets a copy of the structure. So again, that's also significantly different than how Java works, right? Java, everything, when you return a reference from a method, right? It's a reference gets returned. It's not a new version of the object that gets returned. So what does this mean? It means that if you modify a structure, so here we're going to modify T, right? The caller's structure doesn't get modified, right? It's the exact same example from the previous lecture where we tried to swap two integer values, right? If the caller passes in X and Y, their X and Y doesn't get changed, right? So the exact same thing's going to happen here. So here's my function move. It takes in a plain old structure, right? It adds 100 to X, it adds 100 to Y, right? It now returns T. So this one actually returns a value. So here we've got our point P, right? We're going to print out P, so it should be 1 and 2. Then we're going to try to move P, right? If you print out P here, right, you're going to see that P doesn't actually move. Right? So P before the move is 1 and 2, right? So we call move P, so P gets passed up to here. But remember, it's not P that gets passed up, it's a copy of P that gets passed up to here. So T is a brand new structure object up here, right? Its coordinates get changed. So T really does move to 101 and 102, right? But after the move, T hasn't changed, right? Right. So once again, why doesn't it change? It's because when you pass P up to here, right, it's a copy of P that gets passed, right? All the bits belonging to P get copied. That gets transferred up to here, right? That modifies the copy, right? It returns the copy. So in other words, it copies the copy and returns that back to the caller, right? But notice here, I didn't do anything with the return value, right? P can't get changed because it was a copy of P that got passed, right? So P doesn't change here. So what you have to remember that if you're going to try to do things this way is you have to reassign back to P, right? So if you write P equals move P, well, that one now it modifies P, but it modifies P by assignment, right? It's the assignment that changes P here. It's not the function that changes P, right? So when you call when you do it this way, we make a copy of P that comes up to here. So that's one copy, right? The function does some work and it returns T by copy. So there's your second copy, right? And now you have your assignment. So there's your third copy, right? So that one line of code causes 3 copies of P to be made, right? Yeah, it changes P in the end, but you probably don't want to have to copy the object 3 times just to change its X and Y coordinate, right? It does work, but it works because of assignment, not because the function managed to change the coordinates. Okay. The correct way to deal with this is the same way that we dealt with swapping 2 values, right? Instead of passing a structure to this function, you should pass a pointer to a structure, right? Now the function here can actually change the coordinates of the underlying point object itself, right? And then if you call it like that, well, move address of P, it will actually change the object P, right? You don't have to do stuff like that. Okay, so C has this thing called a variable length array, which Java also has, but in Java, everything happens dynamically, so they're not really variable length arrays. So a variable length array is not an array whose size can change at random, right, or at will, right? A variable length array simply means its original length is defined using a variable and not a constant value, right? So you might think that I can make a structure, right, where you have one member is the size, right, and then you make an array using size as your number of elements, right? So this doesn't work in C. Right. C, you're not allowed to have what's a variable length array as a member of a structure. The reason you can't do this is because the C language needs to know how big is one of these things, right? And it actually needs to know a real number. It can't know a variable number here, right? So it's impossible to determine how much memory this thing takes up, right? I know it takes up one of these, so that's probably like 64 bits on my computer, right? But I don't know how much this is, right? That's an array of some variable size, of some variable size. I can't put a number on that size. So this is illegal in C, right? You can't have, the size of a structure must be known at compile time. So that disallows variable length arrays as members of structures. Right? Now what you can do is you can have what's called a flexible array member as long as you only have one and it's the last element of the structure, right? So this is legal, right? This says I have an array, but I haven't said how long it is, how big it is. Right? This is effectively saying the same thing as if you had a pointer to int, right? It's more or less the same thing. It doesn't actually behave the same way mechanically, right? But this is basically using a pointer to an int in this case instead of a regular array, right? If you choose to do this, there's a bunch of things you have to watch out for. I'm not going to go into the details in this course, but if you want to, you can read about it using any of those links there, right? So there is a way to do this sort of thing if you want to do it. It does have some purposes. We're not going to use it in this particular course. I don't think we're going to use this in this course. All right, so that's what you need to know about structures in this course. There are a few important things to remember, right? So when you do assignment or initialization with another structure, it's a copy of the other structure that's happening, right? If your structure has a pointer in it, like this one here, right? And you copy one of those structure objects, right? You get a copy of the pointer. You don't get a copy of the object pointed at, right? If you want to make sure that you get a copy of the object pointed at, you have to do everything manually, right? So in other words, you have to allocate memory for the title. After you copy the object, so after you do your assignment here, right? You have to take I, you have to go to its title member, you have to reallocate a new array. You then have to copy C's title into the new objects array, right? That way you get now you have two independent objects, right? Sorry, you have two objects where their titles are now independent. If you just have plain old arrays, right, then you get a copy of the actual arrays, right? So you really do get two independent objects here. The problem with this approach here is that all of your course info structures eats up this amount of memory, right? So if you have a very short title, you may not need all 256 bytes for the title, right? You only might need 10. And so you end up wasting a bunch of memory this way. All right, any questions about structures? Yes.
That part where you said that whenever you're passing a structure by argument,
yeah,
and it makes two copies, I was wondering how you get the second copy.
So pass P up, so there's one copy here, right? So that now T is equal to P, right? The return, it has to make a copy. So it makes a copy of T, returns a copy of T. So that comes back to here. That's your 2. Now you have an assignment. So that makes a third copy right there. Yeah, 3 copies it. All right, next notebook. So we've done structures, we've done pointers, we're now on to arrays. You might wonder why there's a whole notebook on arrays. And that's because arrays behave differently in C than they do in Java, right? So like in Java, an array is just a container that can hold a fixed number of elements, right? Like in Java, the elements in the array, they all sit beside one another in memory, right? So your array occupies one big chunk of memory and the objects are inside that array. Right? Remember in Java, when you have an array of reference type, the objects inside the array are references, right? They're not the actual objects themselves, right? So in other words, an array of reference type in Java is like an array of pointers in C. Right? The capacity never changes over the lifetime of the array, right? The element type of the array must be specified and you use square brackets. So mechanically, they're pretty similar to what you're used to from Java. There are some differences, right? In Java, you can have a 0 length array, right? So you can make a new array of int by writing new int 0, right? And that's the empty array. There is no empty array in C, right? All arrays in C are of a length at least 1, right? So you have an array in C, you're guaranteed to be able to put at least one thing in it. In Java, you can have an array and you can assign another array to that variable, right? So you make an array of int a, and then you can say a equals b somewhere. You can't do that in C, right? So variables of array type, you cannot assign to them, right? Once they've already, so you can't assign to them after you initialize the array. Right? The big difference that you're going to have to get used to, there's no index checking in C. Right. So you can write code that uses a negative index in C and the compiler, well, I don't know if the compiler will care in this case. I don't think the compiler cares. It'll probably give you a warning, but it won't do what you want it to do. Right. So there's no negative indexing either in C. Right. But there's also no index bounds checking. So you can fall off the end of the array in C and your program will just keep on running. Right. If you're writing into the memory, your program will try to write into the memory past the end of the array, right? If you're lucky, your program crashes and you know there's a problem. If you're unlucky, the program keeps on going along its merry way and all sorts of funny things start to happen. You can't pass an array to a function and a function can't return an array, right? You can write a function that looks like it accepts an array, but in fact, what happens is the function ends up with a pointer instead. So I'll talk more about that later. And similarly, so there is no way to write a function that looks like it returns an array. You have to return a pointer instead. Right. So all this stuff is review again, right? So to declare an array in C, you can declare it, sorry, by writing the element type, then the name of the array, right? Then the size of the array inside of square brackets. So int x square bracket 3 means you have an array of 3 ints, right? And here you really get an array of 3 ints, right? It's not like in Java where you have to write new int 3, right? In C, you've got an array of 3 ints right now, right? There are actually 3 int values in the array. You don't know what values they are, right? So the elements are not initialized, right? So be careful if you make a brand new array and you don't manually initialize the values. They're not equal to 0, or there's no guarantee that they're equal to 0. Right? Assignment works exactly the way it works like in Java, right? Use square brackets. Access works the exact same way it works in Java. Use square brackets. Right? So that prints out 1, 2, 3. There's no bounds checking. So if I write 4 here, something will happen. Right? Oh, the program even seems the program works, right? It prints out 1, 2, 3, but notice what it does, right? It prints out whatever value is sitting after the 3, right? And I have no idea what that value is, right? I guess on my when I ran it this time, it's that value, right? If I run it again, it's some other value. And if I run it again, oh, hey, no, oh, wait, sorry. And if I run it again, it's some different value, right? So you can fall off the end of the array. The language doesn't care. It's your problem, right? So no array bounds checking, right? The reason there's no bounds checking in C is because to check a bounds, that requires an if statement, right? So in other words, it requires your computer to do something, right? The philosophy in C is that the computer shouldn't do anything unless the programmer tells it to, right? So if you want to check the bounds on your array, you got to do it yourself, right? Or more correctly, you have to make sure that you are never going outside the bounds of the array, right? So now the responsibility is on you, whereas in Python and Java, their philosophy is you should be able to detect those kinds of errors at early, right? When they happen, you should be able to detect that they happen, right? So they do runtime bounds checking for you. They're also slower than C because they're doing runtime bound checking for you, right? Okay, the elements are never initialized to any particular value, right? Whatever's sitting in memory is what you get. Now, you have to be careful about this, right? I'm going to run the exact same program, except I'm not going to assign to x0, x1, and x2, right? This is always going to print out 0, 0, and oh, hey, it didn't. Never mind. I lied. So I was going to say it always prints out 0, 0, and 0, but apparently it didn't do it this time. It would not be unusual if it did print out 0, 0, and 0 in this case, right? And you would be misled into thinking it always prints out, it always initializes the elements of the array to 0, right? That's not true, right? So that's another annoyance in the C language, right? The C language says that the values are uninitialized, right? However, the way that the compiler writers may have created this program, may have compiled this program, sorry, is that the memory here might have been set to 0, right? But the standard doesn't say that's what happens, right? So you can write these little toy programs, you'll get one behavior, but the actual behavior is something completely different, right? So remember here, you don't know it's an X, right? Run it over and over and over again, and I guess this time it's always giving me some different values. You don't have to specify the size here, right? But if you don't specify the size, you need to use an initialization list of some kind, right? So when you use an initialization list, that sets the number of elements, and you don't specify the size, sorry, that sets the length of the array. So this makes an array of length 3, sets the elements to 1, 2, and 3. Like that. Right. If you say the size of the array and you use an initialization list, the number of elements in the initialization list must be equal to or less than the size of the array. Right. So here I've got more initializers than elements, so that's an error. Right. You get a warning, you get another warning, and I think you get a failure to compile. Do you? Yes, you get an error here. No, sorry. This actually isn't giving me an error. So this looks like it's just a warning. But it is you can't have more initializers than you have elements. Okay, you can use fewer values though, right? So you can use fewer initializers, right? If you use fewer values, then the remaining elements are uninitialized. This is the case where yes. So on my computer, you always get 0 for the uninitialized values, right? The standard says, I'm pretty sure the standard says that the remaining elements are in fact uninitialized, right? Here, if you run the program over and over and over again, you're always going to get 0, right? But that's not what the language standard says will happen. Okay, so don't forget, strings in C are just arrays of car, right? So strings are just plain old arrays. They have the only difference is that in a correct C string, the last character is set to \0. Right. I guess more precisely, it's set to single quote, single quote /0 single quote. Right. So remember, that's the car that's equal to the numeric value of 0. Right. Now, because they're just array of car, right? If you do something like this, where you go in and set the individual elements of the array, you have to remember to set the last element, or sorry, the last character of the string to \0. Right? If you don't do this, you don't have a null terminated string. All of the string functions may behave badly. Right? So for example, printing the string might behave badly if you don't put in the null terminator. Right? Again, in a little toy program like this always works. I'm pretty sure it always works. Yes, so it always works in a little toy program like this. Right? It's not until you write a real program where this code is sitting somewhere other than the main function where it doesn't always work. Right? So don't forget, if you're going to do this sort of thing, make sure you set the null terminator in the string. Okay, so a few lectures ago, I told you what it meant for a variable to be const. Right? So remember, for a variable to be const, that means the variable is read-only. Right? That's not exactly what it means for an array. Right? So for an array, if you have a const array like this, right, it means the elements of the array are also const. Right? So constant x3 says you have an array of length 3. Right? The first value is always x. The second value is always 2. The third value is always 3. Right? You can look at the values. So I can get x1, which should be 2 in this case. Right? That should print 2. Right? But as soon as you try to assign to any one of the elements, right, now you get an error. Right? And it's pretty obvious what the error is if you read the output, right? Assignment of a read-only location, right? x1. Right? The compiler is trying to tell you, sorry, the compiler. Yes, the compiler is trying to tell you you can't write into this value here, right? Because your array was marked as being const. Right, so you have a const array, you actually have an array of elements that are all fixed. Notice that if you don't initialize the values here, right, there's no way to initialize the values now, right? There's no way to set the values anymore, right? So here, oops, sorry. So here, right, the value of x1 happens to be minus 2 billion, I guess, and something. But there's no way for me to go in and set x1, x2, x0, x1, and x2 anymore, right? So if you're going to make a const array, you have to initialize it at the same point. Otherwise, your array is kind of useless. You cannot assign to an array variable in C. Right? This is awkward when it comes to strings, right? So here's x and y, right? Those are both properly created arrays. They're both arrays of length 3. Right? You would think that you could write something like x equals y. And you would imagine that that takes the bits belonging to y and copies them into x. That doesn't happen, right? If you run that, the compiler, or sorry, if you run the cell, the compiler refuses to compile the program. Right? Read the error message, right? It says assignment to expression with array type, right, is not allowed, right? It's an error, right? So you cannot assign to an array variable in C. The reason you can't do this, or one of the reasons you can't do this, is because C has no way of knowing how long an array is, right? The compiler at this point knows that X is an array of length 3, right? But the fact that X is an array of length 3 isn't kept anywhere in your running program, right? So there's no way for the C runtime to say, oh, X is an array of length 3. It just knows X is an array, right? Similarly here, when it makes Y, it knows to make an array of length 3, but after this point, it doesn't know that the length of Y is 3, right? So here, when you try to do the assignment, it doesn't know if Y will actually, the bits of Y will fit into the array X, right? Because it's forgotten that X and Y are both of length 3, right? Right. So again, contrast that to Java. So in a Java array, it always knows how big it is, right? It has a field called length that keeps the length of the array. That doesn't happen in C. Crazy, but true, right? So that's one of the other big things that you're going to have to get used to, right? If someone hands you an array, you have no idea how big that array is, right? They have to tell you how big the array is. This is super awkward with strings, right? Especially coming from Python and Java, right? So strings are just arrays of car, right? So if I have hello and goodbye, and I would like to make string 1 be goodbye, I can't write string 1 equals string 2, right? Doesn't work. They're just arrays, right? You get the exact same error, right? Error, assignment to expression with array type, right? So that doesn't work either. Again, no one knows how long string 1 is, right? No one knows how long string 2 is. Therefore, no one knows if that assignment is legal or not. Okay. So what do you do instead? So if you want to copy a string, you have to either copy the string manually yourself, right? Or you have to call a function that can copy an array, right? So here, I've got x and y, right? If I would like to copy the numbers from y into x, I have to write a loop, right? So write a loop over the elements of y, copying each element of y into the corresponding location in x, right? Then you can print the array. Notice there's no easy way to print an array in C either, right? If you want to print the elements of an array, you have to iterate over the array, print out the individual elements yourself, right? If you run it, you do in fact see that x does in fact change to 10, 11, and 12, right? Okay, so if you have to copy an array, you should probably use a function instead, right? So in the header string.h, for whatever reason, right? The memory copying function happens to be defined in string.h, right? There is a function called memcopy, right? Now, at this point in the course, this probably looks pretty gruesome to most of you, right? You got a function here, it returns a void pointer here, takes in a void pointer here, takes in another void pointer here, and takes in an unsigned integer there, right? All this is saying is that you've got an array called source, right, that you would like to copy, right? How many bits would you like to copy? Sorry, how many bytes would you like to copy? I would like to copy that many bytes, right? Where would you like to copy them to? I would like to copy them into this array, right? So source array, destination array, number of bytes to copy, right? It returns, I believe it returns it returns dest. So it returns the destination array, right? The only tricky thing you have to remember here is the size, is the count. Count is not the number of elements to copy, right? Count is the number of bytes to copy. More precisely, it's the number of multiples of car to copy, right? So if you want to copy an array of 10 ints, right, you have to compute count as 10 times the size of int, right? If you want to copy 20 doubles, you have to compute count as 20 times the size of double, and so on and so on and so forth, right? So here's how you use memcopy. There's my arrays x and y. Right. Now I'm going to create the variables source and dest so that it matches the declaration of memcopy. Right. So my destination, I would like to copy into x. Right. So I need a pointer. I could just use x, but here I'm going to be explicit about it. I'm going to say I want to copy into x at the first element. Right. So the address of the first element of x. Right. Source is a pointer pointing at the first element to copy, right? So I want to copy y. So I'm going to be explicit about it and say source is going to be the address of the first element of y. You could just write x and y here. Everything would be fine, right? I would like to copy from the source pointer to the destination pointer that amount of memory, right? 3 ints, so 3 times the size of int. Sorry, include string.h. There we go, right? And notice that x is in fact now the array 10, 11, 12, right? I guess we should stop there because we're 20 after the hour, right? And we're only halfway through this notebook, so it looks like we're going to need another lecture to get through this. And so we'll pick this up in the next lecture.